Hello and welcome to the January 2015 Regents Exam in Chemistry. This is a walkthrough of Part B2. This part of the exam consists of 15 free response questions organized into groups of 2 or 3 questions. Here is the first group. These are questions 51 through 53. Base your answers to questions 51 to 53 on the information below and on your knowledge of chemistry. The balanced equation below represents the reaction of glucose with oxygen at 298 K and 101.3 kPa. So they've given us the temperature and pressure conditions, the reactant glucose, and an equation that shows glucose being added to oxygen to produce carbon dioxide and water. This is the standard combustion reaction for glucose. This set of questions involves topic 2, topic 8, and then again topic 2. In the first question, we're going to be asked to find the missing mass. The second question, dealing with topic 8, we're going to evaluate the entropy of the system. And in the third question, we'll be looking at the empirical formulas. Question 51. Determine the mass of carbon dioxide produced when 9.0 grams of glucose completely reacts with 9.6 grams of oxygen to produce 5.4 grams of water. We're given the equation, and we know that our balanced chemical equation has to adhere to the conservation of mass concept. So if we evaluate each one of these things, determine the mass of carbon dioxide produced, that's our unknown quantity, when 9 grams of glucose is completely reacted with 9.6 grams of oxygen to produce 5.4 grams of water. So 9 grams of glucose and 9.6 grams of oxygen represents our reactants, and our products have to come out to the same combined total mass. The algebra for this question is set up over here. So if we add 9 and 9.6 together and then subtract the 5.4 from it, we can figure out what our missing piece is. When the math is done, this comes out to 13.2 grams. So the answer to question 51 is 13.2 grams. Question 52. Compare the entropy of the reactants to the entropy of the products. Remember, entropy is a measure of the degree of randomness among the particles. I've put a little chart together here to help us. If we consider our reactants, the glucose, which is a solid, and the oxygen, which is a gas, you'll notice that in the left-hand side of our equation, on the reactant side, we have 1 mole of solid material, and we have 6 moles of gas material. That's what we're starting with. On the product side, we have 6 moles of gas in the form of the carbon dioxide, but now we have 6 moles of liquid material. Now, entropy is at its lowest when we have the solid form, and it's at its highest when we have the gaseous form. So what we've done in this equation, if we've taken 1 mole of solid and 6 moles of gas on the left-hand side of the equation, and we've altered that so we now have 6 moles of gas, but instead of 1 mole of solid, I have 6 moles of liquid. So clearly we've moved, as we went from left to right, to a situation where we have more entropy. So we're going to condense that thought, and we're going to write in our answer saying that the products have greater entropy. We keep our statements as short as possible when we're writing these free response answers, but we have to make sure to include the key words. In this case, products greater entropy. Question 53. Write the empirical formula for glucose. An empirical formula is the simplified version where we're going to reduce whatever subscripts might be present in the formula to their lowest common form. Glucose is C6H12O6. As we evaluate the glucose, C6H12O6, we can see that all 3 of these values, the 6, the 12, and the 6, are all divisible by 6. So when we go ahead and we divide those numbers, we're going to get the simplified form of this as C1. We're not going to write the 1 because we don't need to write 1s in chemical formulas. H2, and then the O is also reduced to a 1. So our simplified empirical form of this formula is simply CH2O. We'll record that on our answer sheet and move on. Base your answers to questions 54 and 55 on the information below and on your knowledge of chemistry. Diagram below represents a cylinder with a movable piston. The cylinder contains 1 liter of oxygen gas at standard temperature and pressure. The movable piston in the cylinder is pushed downward at constant temperature
until the volume of the oxygen is 1/2 of a liter. So we have a gas trapped inside of the cylinder, and the piston that is now going to be pushed down into the cylinder. So we're going to effectively reduce the volume that gas occupies. Notice it's a sealed container, so nothing's going to escape. Now, 2 questions we'll be answering here involve topic 4, the gas laws, where we're going to be asked to do a calculation, and topic 8, where we're going to be asked to evaluate the effect of concentration on the collision rate. So we have 2 pretty diverse concepts to consider in this set. Question 54. Determine the new pressure of oxygen in the cylinder in atmospheres. When they say new pressure, they mean the pressure after you've pushed the piston down. One thing we want to point out here is that the temperature is not being affected in this particular question. So when we consider our gas laws for this calculation, we're going to use the combined gas law. We can ignore the effect of temperature because it is staying constant in this case. So the relationship we'll be evaluating is the relationship between the pressure and volume, which is represented by the expression P1V1, your starting pressure and volume, is going to always be equal to the product of P2 and V2, the final pressure and volume. Now, for the initial pressure and volume, we're told the conditions are standard temperature and pressure. So we're going to use pressure of 1 atmosphere as our standard pressure. That goes right here. And then we're told that there's 1 liter of gas to start with. The final volume is 1/2 a liter, so we can use this very simple algebraic expression to evaluate what our new pressure is going to be. So our final pressure, P2, after you do the mathematics on this, comes out to 2 atmospheres. So we'll simply go back and put our answer in. The answer is 2 atmospheres. Question 55. State the effect on the frequency of gas molecule collisions when the movable piston is pushed farther downward into the cylinder. So we have oxygen gas molecules trapped inside this cylinder, and the piston, which is sealed, keeps them compressed inside there. The idea here is that if we push this piston downward, what's going to happen to the chances of the oxygen particles bumping into each other? Looking at this small diagram, the top picture represents the piston when it's in its 1 liter position. The blue dots representing the oxygen molecules. If we reduce the volume to 1/2 of a liter, you can see the amount of space the little blue oxygen molecules have to occupy is much smaller. So what should happen to the chances of them bumping into each other? Well, they have less space in which to operate, so we would expect to see them bump into each other more frequently. So our answer is going to be expressed as increased frequency. So any sentence that you write in this answer should include the terms increased frequency or more frequent collisions or something to that effect. Base your answers on questions 56 through 58 on the information below and on your knowledge of chemistry. Here we're given a chart, and it has the formulas and boiling points at standard pressure for several substances: ethane, methane, methanol, and water. 3 of these substances are organic compounds, and their formulas are shown here. And of course the boiling points are all presented for you. Now we're going to be asked to analyze this information in 3 different questions. From topic 6, we'll be asked to discuss the intermolecular forces among the particles. And from topic 4, we're going to be asked to explain the energy changes that are associated when these things change phases. And then a combination question from topics 6 and 7 will be asked to discuss the bond polarity within these substances with regard to their ability to dissolve. So let's get started. Question 56. Identify the compound that has the strongest intermolecular forces. Well, this is going to be a pretty easy question to figure out. But first of all, I just want to show you the question is what I call an extreme question. They're asking for something that has the strongest intermolecular forces. That would be like asking which has the weakest intermolecular forces, an extreme question. And since we're going to be comparing numerical data here, what we're going to do is we're going to throw out the 2 numbers that are actually mid-range numbers. The highest number we see is the 100, and the lowest number we see is the negative 161.5. So automatically I'm throwing out the mid-range answers because I have an extreme question. So it's either going to be the water or the methane. Now, what exactly does it mean when something is boiling? Because we have the boiling points here. Well, boiling means that you're going to get the particles to separate and fly away from each other and go from being liquid to being a gas. Now, if they're holding on to each other really tightly, that's going to be a harder, more difficult challenge to get them to separate from each other. So we would expect the substance with the higher boiling point, in this case water, is probably the substance whose particles are holding on to each other with the greatest intensity. That intensity of particles holding on to each other is our concept of intermolecular forces. So the higher boiling point here indicates the substance that has the strongest intermolecular forces. Our answer is simply water. Question 57. State the change in potential energy that takes place in a sample of methane as it boils at negative 161.5 degrees Celsius, its boiling point. Keep in mind that when something is boiling, its temperature actually does not change. It stays constant until the entire substance has been boiled. So make note, the temperature is not changing in this case, because temperature measures kinetic energy. So we can also say that kinetic energy is not changing. Well, all this energy is going somewhere because the substance is being heated. Energy is being absorbed by this substance in order to change the phase. So the only explanation would be that the potential energy of this substance is increasing. So any phase change that involves the addition of energy is going to involve the increase of potential energy for the particles in that substance. Question 58. Explain in terms of molecular polarity why the solubility of methanol in water is greater than the solubility of methane in water. Well, at the center of this issue is the concept, when we're dealing with solubility, is that like dissolves like. So if you have substances that have similar polarity, you're going to have a very good interaction in terms of their ability to dissolve. So let's analyze the molecules in question up here. The methane molecule is a tetrahedral shape, very symmetrical, and because of its symmetry, it is a non-polar molecule. Our methanol molecule, quite different. It has the somewhat tetrahedral shape, but on one side of the molecule, instead of having hydrogen, it has a hydroxyl group. That side of the molecule is going to be a greater attractive force for the electrons. Thus, we're going to have an uneven distribution of electrical charge, and we have a polar molecule. Water molecule, very well documented as being polar, with the negative orientation on the oxygen side and the positive orientation on the hydrogen side. So that's also polar. Now, concept being that like dissolves like, you can see why the methanol has a greater tendency to dissolve in water, because it is more like the water in terms of its molecular polarity. You could say it that way. But let's just summarize a little bit more. Water is our solvent. It's a polar solvent. And our two potential solutes, methane and methanol, have different polarities. The methane is nonpolar. And when you combine the nonpolar solute with the polar solvent, you get an insoluble mixture. Methanol, on the other hand, being polar, similar to the water's polarity, is going to give us a soluble dissolution process. So, in summary, and to construct our final answer, methanol and water molecules are polar. Methane is nonpolar. That's the specific reason why methanol and water dissolve better than methane and water. Base your answers to questions 59 through 61 on the information below and, of course, your knowledge of chemistry. Here we have some diagrams that represent ball and stick models for two molecules. In a ball and stick model, each ball represents an atom, and the sticks between the balls represent chemical bonds. And we're dealing with two elements here, hydrogen and carbon, the carbon represented by the open circles and the hydrogen represented by the closed dot structures. So here's diagram A, our first molecule, and diagram B, our second molecule. They're both organic molecules made of carbon and hydrogen. They are hydrocarbons. Three questions we'll be analyzing here. The first one brings a little bit of the bonding unit in, and they're going to ask us to draw a dot structure for the element carbon. That'll be easy enough. Then we go to topic 11, the organic chemistry unit. We're going to be asked to explain the term saturated hydrocarbon using the diagrams, and then also to explain the term isomer referring to the diagrams. Question 59. Draw a Lewis electron dot diagram for an atom of the element present in all organic compounds. They, of course, are referring here to carbon. And since we're drawing the diagram for an atom, we assume that it is also a neutral atom. It does not have a charge, so it will have an equal number of protons and electrons in its structure. Hopefully you recall that electron dot diagrams begin with the symbol for the element, which in this case carbon is just going to be a C. And then we can see from our periodic table, we need to know how many electrons are in the valence shell of carbon. The electron configuration is this little set of numbers at the bottom. It has a total of 6 electrons, 2 in the first energy level and 4 in the outer energy level or valence shell. We'll ignore the 2 that are in the inner or core part of the atom, and we're only going to put dots to represent the valence electrons. So our diagram needs 4 dots. Now, usually when we have a 4-dot diagram, the configuration is to put the first 2 together on top, indicating a pair in an orbit, and then we put the third to the right and the fourth on the bottom. That's a good standard way to draw it. The regents would also accept, according to their answer key, they'll accept any diagram with 4 dots around the letter C. So even if you hybridize the orbits and spread out your electrons like this, you'll get credit for that. The key is, though, 4 dots around the letter C. Question number 60. Explain in terms of carbon-to-carbon bonds why the hydrocarbon represented in diagram B is saturated. Okay, here's your diagram B hydrocarbon. Here's your diagram A hydrocarbon. Whether something's saturated or not has to do with whether or not the carbon atoms have single or double or multiple bonds. Now you can see in both diagrams, all the bonds that are shown are all single bonds, the single lines representing the bonds in both cases. So whether you're talking about diagram B or diagram A, the statement would be the same. Both of these are saturated hydrocarbons because they have no multiple bonds or double bonds. The answer then, the molecule in diagram B has only single carbon-to-carbon bonds, period. That's why it is saturated. If there had been a double bond, so if the picture had something in it that looks like this, this would be an unsaturated hydrocarbon because it has a double bond in its structure. Question 61. Explain why the molecules in diagrams A and B are isomers of each other. Well, to be an isomer, a structure has to be put together differently but made of the same materials. So let's clarify and verify here that these two diagrams are truly made of the same materials. If you count carbon atoms, we see 2, 3, 4, 5, and 1, 2, 3, 4, 5, so they both have 5 carbons. And we count up the little hydrogen atoms. You can count them as easily as I can, and you'll find that there are 12 on each structure. So in both cases, we have 5 carbons and 12 hydrogens. However, these molecules are constructed differently. In this case, the carbons form a chain that is 5 carbons long. And in this case, you don't see a 5-carbon chain. You see perhaps a 4-carbon chain with 1 carbon stuck off to the side. That's a completely different structure. So to summarize, the molecules have the same molecular formula of C5H12, but different structural formulas. In other words, they're put together differently. And that is why they are isomers of each other. Base your answers to questions 62 and 63 on the information below and again on your knowledge of chemistry. The nuts, bolts, and hinges that attach some gates to playground fences can be made of iron. The iron can react with oxygen, so we're talking about a chemical reaction between iron and oxygen happening in the air, and the unbalanced equation representing the reaction is shown here. So we are given an equation. We're told that it's not balanced yet. You can almost see where this is going. So in the first question, we're going to be asked to balance the equation. We'll do that by inspection. And then in the second question, we're going to be asked to evaluate this equation on the basis of its oxidation and reduction half reactions. Question 62. Balance the equation in your answer booklet for the reaction using the smallest whole number coefficients. So they've taken the formula, they put it into your answer booklet with little lines in front of each of the formulas so that you can balance it. Now I'm going to take this opportunity to review balancing equations using a method that I like to call the inventory method. You undoubtedly at this point in your chemistry career have been shown how to balance an inorganic equation such as this one. This is pretty straightforward, but it has a couple little tricks and turns to it. What I do is I put a list of all the elements that are being balanced underneath the arrow. and treat the arrow like an equal sign. And we have to finish this by making sure we have the same number of each type of atom on both sides of the equation. We can alter those numbers by putting coefficients into the blanks to balance the equation. Just keep in mind, any number you put in these blanks will serve to multiply whatever it's been placed in front of. So let's get started. First thing we do is we count to see where we're starting. And right now I see 1 iron on the left and 2 oxygen atoms on the left. On the right side of the arrow there are 2 irons and 3 oxygens. There you have it. So everything's messed up, the iron and the oxygen. Where should we start? It doesn't really matter. It's a process. It's kind of like a tennis match. We're going to be going back and forth until we get it to perfectly balance. I'm going to start with the oxygen, however, because the numbers 2 and 3 instantly tell me that we can't just increase one side because the left side goes up in 2s. So if I double the left side, which is all I could possibly do is to put a 2 here in front of the O2, that's going to change that to a 4. That'll be too much. I'll have to go back to the other side and increase that, and that'll be too much. I'll have to come back to the other side. So little shortcut. The shortcut method I use is called the least common multiple. You might remember it from math class, LCM, least common multiple. And the least common multiple of 2 and 3 is 6. So I'm going to force these numbers to become 6. For the oxygen, since there are 2 of them present, I'll multiply that by 3. That changes my oxygen to 6. Great. On the right-hand side, I have 3 oxygens. If I multiply that by 2, that'll give me 6 of those. Super! So now I have matching oxygen atoms. But note this. When I put the 2 in front of the O3 to make it 6, I inadvertently changed the iron to 4. I've doubled the F2, and making that 2 times 2 will be 4. So I now have 4 irons on the right, still only 1 on the left. Very easy to fix. Because iron stands alone, all I have to do is put a 4 in front of it, and that will change the iron to a 4 without messing anything else up. So you see our inventory now matches. 4 irons left, 4 irons right, 6 oxygens left, 6 oxygens right. We're done. So let's transfer those numbers to our answer sheet. And we're going to finish this question by putting a 4, a 3, and a 2, and that will look perfect and everyone will be happy. Question 63. Determine the change in oxidation state for oxygen in this reaction. Oxidation state assignment is a very specific skill that comes into topic 9, and there's a set of rules for assigning oxidation states under various conditions. So we're going to analyze oxygen. You can see oxygen's 2 situations are here and here. In the first case, our oxygen is not combined with anything. In the second case, it is combined with the iron. So we want to see what happens to its oxidation state as it goes from one situation to the other. So let's transfer this information over to a little set of rules that I've brought in for this purpose. In the first case, our oxygen is O2 by itself. And in the second case, it's part of a compound, Fe2O3. So let's interpret from our rules. From a very trusted source, we know that every uncombined element has an oxidation number of 0. Well, that kind of answers the question. Our oxygen is going to start with an oxidation state of 0. There's an example here in the chemical equation. 2 sodiums plus chlorine yields 2 sodium chlorides. Both the uncombined sodium and the chlorine would be assigned oxidation states of 0 in that case. Now, in the second situation, our oxygen is combined with iron. Oxygen is usually -2 in compounds, but there are exceptions to this. When it is combined with fluorine, which is more electronegative, it actually has a +2 charge. And when oxygen is -2 in water and +2 in OF2, in the peroxide ion, which is a polyatomic ion that involves oxygen, oxygen actually has a oxidation state of -1 in that case. Well, this is going to be a regular -2. It's not one of the exceptions because we're not combining with fluorine and we're not using oxygen in peroxide state either. So we're going to be going from 0 to -2. Let's go back and fill in our answer. Oxygen starts with an oxidation state of 0 and it winds up with an oxidation state of -2. There's your completed answer. Base your answers to questions 64 and 65 on the information below and once again our knowledge of chemistry. The pH of various aqueous solutions are shown in a table. So we have a table here. We have pH values, so we're dealing with acids and bases. pHs of 2, 3, 7, and 12. already the bells should be going off in your head, realizing that 2 and 3 are low pHs, 12 is a high pH, 7 is neutral. Hopefully that comes to mind very quickly for you. Now our actual solutions involve HCl, that's hydrochloric acid, C2H3O2, a little bit more obscure, but that's acetic acid, which you could find actually on your reference tables. Sodium chloride, it's going to be a salt, and sodium hydroxide, that's going to be our base. So the two questions, both from the acid-base unit, we're going to use table M, and we're going to identify the color of certain acid-base indicators for these solutions. And also from topic 10, we're going to be asked to explain the pH scale. So let's get going. Question 64. Complete the table in your answer booklet by writing the color of thymol blue in the sodium chloride and in the sodium hydroxide solutions. So this is what's in your answer booklet. You just got to write the names of the colors that go here. We're dealing with thymol blue. So if we go to our acid-base indicator chart, the thymol blue colors are either yellow or blue, depending on the pH. On table M, you're given a pH range. Generally speaking, if the pH that you're analyzing is less than the bottom number, then the color is going to be the left-hand color. So anything with a pH less than 8 is going to be yellow, and anything with a pH greater than 9.6 is going to be blue. There's somewhat of a transition zone between 8 and 9.6. It wouldn't really be fair to ask you what color to expect. At any rate, we're analyzing the sodium chloride. We're told that the pH is 7. So 7 being less than 8, we're expecting a yellow color for sodium chloride. And for our sodium hydroxide, whose pH is 12, that's clearly greater than 9.6, so we expect that one to be blue. So sodium chloride yellow, sodium hydroxide blue. Sodium chloride yellow, and your sodium hydroxide solution blue. So that's the way you would record the correct answer for question 64. Question 65, the final question in the set. State how many times greater the hydronium ion concentration in the hydrochloric acid is than the hydronium ion concentration in the acetic acid. Well, the pHs for these two things, the hydrochloric acid has a pH of 2, and the acetic acid has its pH of 3. So what exactly does that mean? Well, don't know how deep you might have gotten into the mathematics of pH, so I'll give you the complicated answer and the simplified answer as well. The pH is a measure of the negative logarithm of the concentration of the hydronium or hydrogen ion concentration. Since the hydrochloric acid has a pH of 2, we can then figure out the hydrogen ion concentration by just taking that pH value, putting a minus sign in front of it, and expressing it in molarity terms, in this case as 1 times 10 to the negative 2. The second substance, the acetic acid, whose pH is 3, is going to generate a hydronium concentration of 1 times 10 to the minus 3rd. Notice that the position of the pH value is in an exponent over the number 10. So when you change the exponent over the number 10 by a value of 1, you're actually changing the value of the term by tenfold. So 10 to the negative 2 is actually 10 times larger than 10 to the negative 3. Let me simplify this for you. Each point in the pH scale represents a tenfold change in concentration. That's what we're really saying here. So, how do we write this out? How many times greater is the hydronium concentration in hydrochloric acid, whose pH is 2, than the hydronium ion concentration of the acetic acid, 3? Well, since they vary by 1 point, the difference is a tenfold difference, with the lower number actually representing the higher concentration, because remember, these are negative exponents. So, the hydrochloric acid is 10 times more concentrated than the acetic acid would be. Now, that concludes Part B2 on the January 2015 Chemistry Regents exam. Please look for additional videos for Parts A, B1, and C of this exam. Thanks for watching. You can access additional videos and materials for this and other chemistry exams at alchemtutor.com. For questions, comments, or permissions, please contact me at asnyder@alchemtutor.com. If you have interest in contracting tutorial services, you can also contact me through the website at alchemtutor.com.